Alright, this is our lab on measuring the concentration of an unknown, and we're going to use the Beer Lambert law to do this. The first part of the lab is to calculate the amount of copper chloride that we need to weigh to make our stock solution. So the idea in the lab is to prepare a stock solution of 0.4 molar copper 2 chloride, and we're going to prepare 35 milliliters of that solution. And then once we have this 35 milliliter made of stock solution, we're going to prepare 5 dilutions. These test tubes number 1 to 5, actually the first one is not a dilution, it's just 10 milliliters of our stock solution and 0 milliliters of water. But then from test tubes number 2 and then 3, 4, and 5, we're going to dilute the stock solution, 8 milliliters of stock plus 2 milliliters of water, 6 of stock and 4 of water, 4 stock, 6 water, 2 stock, 8 water. So you can see when we do these dilutions that the total volume after the dilution is always going to be 10 milliliters. So the very first thing we need to do is to figure out how much calcium chloride to weigh. We know that the concentration is equal to the moles per liter. And in this problem, we have the concentration at 0.40 molar, and we have the volume at 35 milliliters. And so we need to convert the 35 milliliters to liters. So we divide by 1,000 and we get 0.035 liters. So then we can find the number of moles that we need to prepare the solution. And once we have X moles of CuCl2, then we can take the moles and multiply by the molar mass of CuCl2 to get the mass. So we're going to get the number of moles that we calculated here. We're going to multiply by the molar mass of copper chloride, and that will give us the number of grams of copper chloride that we need to prepare the solution. Okay, so I'm going to go ahead and prepare this. Okay, so I'm going to zero out a container, and then I'm going to add the copper chloride now that I've carefully measured or calculated the amount that I need. I'm going to weigh that amount very carefully. Perfect. And then we have to use this copper chloride to make 35 milliliters of solution. So we're not adding 35 milliliters of water, we're making 35 milliliters of solution. So we're going to need a little bit less than 35 milliliters of water. So we're going to start by pouring some water in here. And we're going to make our solution, which means we're going to dissolve the solute. Once the solute is all dissolved, we're going to pour this into our graduated cylinder. We're going to rinse this with some more water. always making sure that we stay under 35. Okay. And now what we're going to do is we're going to add more water until the volume of the solution totals 35. There we go. So now we have 35 milliliters of the copper chloride solution. It is time to start making our dilutions using our stock solution. So we're ready to go. With the dilutions, we have the 35 milliliters of the copper chloride solution, 0.4 molar. We have 5 labeled test tubes. In the first one, there's no water. Test tube number 2 has 2 milliliters of water. Test tube number 3 has 4. Number 4 has 6. And number 5 has 8 milliliters of water. So now we're just going to add the copper chloride solution, and we're going to follow the lab handout over here. So in test tube number 1, 10 milliliters, and then 8, 2, 6, 4, and 2 in the other test tubes. So we have 10 milliliters in the first test tube. And then we're going to put 8 milliliters in the second. And 6 in the third, 4, and 2 in the fifth. Our dilutions are made. And now we have to take the absorbance of each one of these solutions. So after calibrating the colorimeter with a cuvette of water, the colorimeter is set at 635 nanometers, and this is the wavelength of the red color, because the blue solution will absorb the red. We're going to start with our most diluted solution, which is test tube number 5. And what we're going to do is we're going to fill the cuvette with that solution. And this is just a rinse. We're going to discard that, and then we will fill it up again. And then we're going to measure the absorbance of that. So we're going to make sure that the clear sides of the cuvette are lined up with the path of the light. Close the lid and look at the absorbance value, 0.092. And so this is the absorbance for test tube number 5. And we're going to continue like this test tube number 4, 3, 2, and then 1. Always giving the cuvette a rinse with that solution first, then filling the cuvette now with solution test tube number 4, and reading a value for this 0.168. So now that I've recorded all my absorbance values for all of the test tubes, I have to calculate the concentration. And the idea here is that we have to do a calibration curve, and our calibration curve is going to have absorbance on the y-axis and the concentration on the x-axis. So I have to figure out what the concentration for all these diluted solutions were. The first one is easy because in test tube number 1, we started with the stock solution that is 0.4 molar, and we didn't add any water to it. So therefore, the concentration remained at 0.40 molar. But then the other test tubes, we did add some water. And so when you add water to a stock solution, what you're doing is you're diluting the stock solution. And so since it's a dilution, we can use the dilution equation to calculate the final concentration. So this is trial number 2. And the dilution equation is M1V1 is equal to M2V2. Now, concentration and volume in the original state, one means before we added the water. So what was the concentration of the solution before we added the water, and what was the volume of the solution before we added the water? So for test tube number 2, before we added the water, we had 8 milliliters of 0.4 molar copper chloride. So this is the situation before we add the water. Concentration 1, 0.40 molar. Volume 1 is 8 milliliters, so 0.008 liters. And this is equal to situation 2, which is after we add the water. Well, the concentration after we add the water, that's what we're after. Now, what was the volume after we added the water? So what we had in the test tube number 2 is 8 milliliters of the copper chloride. And then we added 2 milliliters of water. So what was the volume in the test tube after we added the water? Was the 8 plus the 2, which gives us a final volume of 10 milliliters. So volume 2 is 0.010 liters. And then we solve for M2, which is the final concentration. That's what we're looking for right here, M2. You repeat the same calculation for all the test tubes, and then you have your concentration, you have your absorbance, and you can make your graph. Hey, we're about to unleash the magic of Excel here. I know you love Excel. All right, so we're going to make 2 columns. The concentration, column A. Remember, Excel does it alphabetically, X, Y. So x-axis is concentration. And so we calculated these concentrations for our test tubes. And so we're just going to enter those real quick. And in the next column, the corresponding absorbance. To make the graph, we just select both columns, and we are going to insert a scatter plot, and we're going to pick the one with just dots because we're going to actually add the trend line. So we're going to click on that, and so we have our values. And so to get the trend line on this, we're going to right click on one of the dots, and we're going to select the add trend line option. And in the trend line menu, we are going to turn you over a little bit. In the trend line menu, we're going to set the intercept at 0, 0. And display the equation of the slope. So when that's done, we can give our our graph a proper title and label our axis. Now that we have the equation for the best fit line, this is our calibration curve. It is the value of the absorbance versus concentration of CuCl2, and our concentration is in molar. No unit for the absorbance. And since we have only one line here, we don't really need a legend for this. Our trend line disappeared. All right. Now using this graph, and this is what we're going to use to determine the concentration of the unknown. At this point, now that we have the graph, we're going to get the sample of the unknown and measure its absorbance. And so using our graph, we're going to use the slope equation, or we could use the graph as well, and say, for example, that the absorbance of the unknown is 0.2. So we're going to go at 0.2 on the graph, and if we draw a straight line to meet the curve, and then just go straight down from there, then that will give us the concentration of the unknown, which had an absorbance of 0.2. Now to get a more precise number, so this is going to give us a ballpark estimate. To get a more precise number, we're going to use the graph equation, because the y value on our graph is the absorbance. So if the unknown has an absorbance of 0.2, then y will be 0.2. And that's going to be equal to 1.0693 times x. And x is the value of the concentration that we're looking for. And so therefore we can solve for x, and that way we will know the concentration of the unknown solution. That's it. So I hope you're successful in your lab. Good luck.